So I'm Susan Clark. I'm an assistant professor at Stanford in the physics department and also part of our Kavli Institute for Particle Astrophysics and Cosmology, or KIPAC. And I want to talk to you today about how and why we map cosmic magnetism, which is to say astrophysical magnetic fields, in particular in the space between the stars in our galaxy. So I'm hoping that this will be, I was told this is informal, and this is a bunch that likes to ask questions. I've already had some great conversations with people outside, so please, I'm trying to keep this informal and interactive. Feel free at any point. But the broad questions that I'm hoping to give you at least a good intro to today are, first of all, where we find astrophysical magnetic fields. The short answer is basically everywhere. What is the interstellar medium? What is this environment where most of my research is focused on studying these interstellar magnetic fields? And then how is it that we can even begin to study, to measure these very weak, ghostly magnetic fields way out in interstellar space? So I hope by the time you leave here today, you can describe to your friends at least a few of the ways that we measure interstellar magnetic fields.
No equations.
And no equations. And yeah, that's right. I'm going to try and keep this pretty high level. I understand we have a whole range of backgrounds, so I'm going to try and, for the most part, give you a nice broad overview, occasionally dip into something slightly more technical for those that like that, but we'll always come back. Okay, and just to get us started on an absolutely non-technical note, I think this is a fascinating subject astrophysically, but magnetic fields in general are something that have fascinated humans for a very long time. I love this quote that's attributed to Aristotle, but he was actually attributing it to philosophers that came even before his time, that these very early philosophers would observe particular types of rock that are permanent magnets and describe them as having a soul because of their ability to have this magnetic influence. And now these days, of course, that's not how we describe this phenomenon. We talk about magnetic fields, which is our mathematical, physical description of this magnetic force that acts on charged particles or currents or chunks of magnetic material like this paperclip. And you might, in an astrophysical context, be most familiar with magnetic fields associated with compact objects. So I figured we'd start there. You probably know that the planet we're sitting on right now has its own Earth's magnetic field that is generated and sustained by electric currents from the motion of the liquid metal core, actually liquid metal outer core, in the interior of the Earth and the Earth's rotation. And that magnetic field is handy for lots of reasons, right? If you are very, very lost and have no satellite signal, you could use your compass, and you could use the needle on your compass is turned by this planetary magnetic field. It's also very much keeping us alive right now. The fact of this planetary magnetic field acts as a very nice shield, deflecting lots of very high energy harmful radiation that comes off of the sun. And the fact that our planet has a magnetic field helps us be protected from that and helps us hang on to our atmosphere, which obviously is also quite useful for harboring life. So people think about, astrophysically, people think also about planetary magnetic fields as maybe an important component of planetary habitability, for example. And planets aren't the only ones, right? Stars, like our sun, are also home to magnetic fields and very rich magnetically driven phenomena associated with their stellar magnetic fields. But we're going to talk today about really none of that. We're going to take our focus to even larger scales and to much more diffuse environments and talk about the magnetic fields that are associated with galaxies themselves, with the diffuse gas that exists within galaxies, like our Milky Way. Although this is obviously, these are real data and obviously not an observation of our Milky Way, because we would need to leave the Milky Way to take its picture, and we can't do that. But the point, the reason I'm showing you this is a spiral galaxy that, much like our Milky Way, is a spiral galaxy, meaning it has a pancake disk that we're looking here face on, and we see these beautiful spiral arm structures. And what we observe here in these yellow lines, these are measurements that I will explain soon how we made, but these are measurements of the magnetic field orientation in the gas in this galaxy. And the point is that galaxies themselves are home to these very large-scale ordered magnetic field structures that influence a lot of the physics of what goes on within galaxies. But I also thought that to start us off here today, I would give you a quick sense of just the relative strength of the magnetic fields that we're talking about astrophysically as compared to maybe your everyday experience. So here's your everyday experience. Maybe a common interaction for you with magnetic fields is to stick your A+ homework or your kids' awesome drawing or something to your refrigerator using a magnet, right? Using a refrigerator magnet. And so cartoonishly here, I've drawn us a number line in powers of 10, okay? So each of my little tick marks is a factor of 10 in magnetic field strength, either stronger than our refrigerator magnet or weaker than our refrigerator magnet. So here, this is 10 times stronger than the refrigerator magnet, 100 times stronger, etc. Right? And so my question to you is, oh, by the way, this is interactive. Where do you think we should plot the magnetic field at the surface of the Earth? So maybe either point that way for weaker or that way for stronger than our refrigerator magnet. Yeah. This is a log scale, yes. Yeah, fantastic. So our fridge magnet, a typical strong-ish one, is order 100 Gauss. And exactly, the magnetic field on the Earth's surface is quite a bit weaker than that, approximately 100 times weaker than that, right? Half a Gauss is a typical magnetic field strength. Sorry?
It's stronger than I figured.
Stronger than you figured, yeah. Well, there you go. And okay, and then if you had to guess, let's put the magnetic field of our galaxy at the approximate location of the sun, which is around where we've measured it the best, relative to the Earth. Do you think we're going that way or that way? Weaker or stronger? Of interstellar space nearby to the sun. Yeah. Typical chunk of interstellar space. Yeah, everyone's mostly pointing weaker, and that's exactly right, and quite a bit weaker. So the typical interstellar magnetic field strength, as we've measured it in a typical chunk of the interstellar medium nearby to the sun, is of order a few microgauss. So we're talking about just a few parts per million as strong as the Earth's magnetic field. But it turns out that, yes, please.
How in the world could you measure that in the vicinity of the sun?
Yes. That's a great question. I'm going to talk about a few of the different ways that we measure magnetic fields, but actually the best way that we have to measure the magnetic field strength, which is for the most part where this number is derived from, is to measure what we call Zeeman splitting of particular spectral lines. So in astrophysics, a good fraction of the information we have to work with comes to us in the form of light, one way or another. We're observing particular spectral lines, so emission that's associated with a particular quantum transition in an atom or a molecule.
And the sun isn't impacting that measurement?
That's right. This is a measurement that we're making in the diffuse interstellar gas. When I say in the vicinity of the sun, I mean within, let's say, a kiloparsec of the sun. So it's a very large vicinity. Yes, thank you. Although we can use that same technique to measure magnetic fields on the sun itself, but the sun's magnetic field is much stronger. Great. And then just for fun, we can also point out that astrophysics manifests just a bewildering range of magnetic field strengths. So we can also put magnetars on this plot, these remnant neutron stars that have these very, very powerful magnetic fields that power all sorts of bizarre phenomena. But we're going to focus on the far left end of this number line today, where we're talking about the magnetic field that is just a few parts per million of the field strength of the magnetic field on the surface of the Earth, but pervades this medium within our Milky Way galaxy and influences the dynamics of the material that is constantly moving and changing and evolving our galaxy and similar galaxies. So to understand what I mean by this, we need to talk about where we are focusing here, which is the interstellar medium, or the ISM, as astronomers creatively call it. Actually, I've always thought this was kind of a horrible name for the thing that I study, right? It's literally named for what it's not. It's just the not stars medium, right? And that, I mean, it seems bizarre, right? I'm sure people that study, ocean currents don't refer to what they study as like the stuff between the whales, right? It has its own name.
Okay, but do you have a name in mind you'd like to use?
Good question. No, I should really come up with one. I should really. That's true, but that has a complicated history as a term. Yeah, maybe you'll all have to ruminate on that and tell me if you come up with a better name. For now, I'm just here to complain. Great, but this medium is quite literally all of the stuff between the stars in galaxies, which it turns out is a very rich phenomenon. So to dip just ever so slightly more technical for a minute, you may have seen a version of this pie chart on the left. I think you had a talk by Lena Nassib here pretty recently, or I'm sure you have people coming here to talk about dark matter and dark energy all the time. And the takeaway from this plot is, of course, that dark matter and dark energy constitute a large fraction of our universe, and there's a lot to figure out about that. But within this slice of the universe that is made up of ordinary matter, everyday matter, we also have to understand how that is distributed into various components of gas within and between galaxies. And we've done our job. We have a decent idea, although these percentages are very approximate, about how this normal matter is distributed into things like stars, things like cold gas, things like hot, very tenuous plasma that surround galaxies, and the even more diffused gas that we find in the space between galaxies, which you could probably guess this term, we call the intergalactic medium. But so we are talking here today about the few percent of the few percent, the gas, and as it turns out, also dust, that it populates the space between stars within galaxies like our Milky Way. And so I'll take you now on a brief tour of the various constituents of the interstellar medium. What is it that makes up this space between the stars in the Milky Way? And the very first thing is that there is a good amount of interstellar gas. So a lot of the space between the stars is well, the space between the stars in general is not empty. On average, in just a typical chunk of your interstellar space, that you'll have at least about an atom per cubic centimeter. That's unbelievably dilute compared to even the absolute best vacuum that we can create on Earth. But that space is full, and in particular, there is a good amount of gas. So what you're looking at here are observations of the whole sky. So often astrophysicists will show you images of the whole sky at once by projecting every direction in the sky into something flat that we can show on the screen. So just in the same way that you might take your globe of the Earth and project it to make a flat map that you can put on a placemat, that's what we're doing here. We're looking in every direction, but then projecting into this particular projection here. So this bright part in the middle here, this bright stripe, what do you think that is if this is looking in every direction at the gas around us? That's a galactic plane. Yeah, exactly. That's that pancake disk of our Milky Way galaxy. And then these are in coordinates that put that in the center. So these are in some galactic coordinates such that you can look above or below the plane and be looking out into the more, up out of the galaxy into more diffuse regions. Yes?
When you say gas, you mean neutral gas as opposed to plasma?
Yes, thank you. In this case, that's exactly what I mean. So this is in specific an emission line of ground state atomic hydrogen. So extremely abundant neutral atom. Atomic hydrogen, as you know, or as you may remember, one proton, one electron. Both of those are associated with a spin. And there's a photon with a characteristic wavelength that corresponds to the energy difference between those spin-aligned and spin-anti-aligned states. That photon has a characteristic wavelength of just about 21 centimeters. So, something like this. And so we call this the 21 centimeter line of neutral hydrogen. Astronomers will also refer to this as H1 for some historical reasons. And this is possibly my favorite line, although I've never thought of it as having a favorite until just now. But I have done a lot of research, a lot of work using data measuring exactly this emission line, because this neutral hydrogen is ubiquitous in the interstellar medium, and it's a great way to probe the physics of the relatively cold regions of interstellar space. And so here I couldn't resist showing you a movie of some of these data. This is the measurement that we make. We measure the line emission from this particular spin flip transition of ground state atomic hydrogen. We measure that emission as a function of position on the sky, and also as a function of Doppler shifted frequency, because the gas is in general not perfectly at rest with respect to us, and so we measure not exactly that 21 centimeter wavelength, but a slightly red shifted or blue shifted line depending on our relative motion to the gas. And that means that we can create movies of our data because our data are three-dimensional, right? We have two spatial dimensions and one dimension of spectral frequency. Does that make sense? You with me on this? Okay, awesome.
What's the source? What's stimulating the radiation? What's pumping the atoms?
In this case, we think that in general, in the diffuse ISM, that even just the CMB is enough to populate the upper state of this transition, and so this is really generically available to us to observe. And so what you're seeing here specifically are measurements from the Arecibo radio telescope, which, moment of silence. But this is showing you basically the whole sky as was visible from above Arecibo. I say moment of silence because it very tragically collapsed a few years ago. But before that, it was a phenomenal facility. And so you're seeing basically the sky as visible from overhead of Puerto Rico, where that telescope is located, panning across your screen. So imagine that the Earth is turning and the sky is moving overhead of you. And then you're also moving back and forth along this Doppler shifted frequency space. And you see all of this just incredible detailed structure that, it turns out, in my own work has taught us a lot about the relationship between the interstellar magnetic field and the structures of gas that exist in the diffuse interstellar medium. It's also taught us a lot about the density and thermal distribution of this gas and all sorts of other fascinating physics.
What was that very active region on your previous slide?
Oh! This! Yeah! Wait, yeah, who said Magellan system? Exactly. Yeah, that's exactly what it is. Well done. This is the Magellan system. So this is the large and small Magellan clouds, two galaxies that are interacting with the halo of our Milky Way galaxy. And they appear bright orange here because this is color-coded by this Doppler shifted velocity of the line. And so they are moving at quite anomalous velocities relative to our local standard of rest. And so they're all the way over here on the orange end of our velocity scale. So that's why they pop out at you. Yeah, good question. Thank you. I meant to mention those. Wonderful. Let's see. What else should we talk about? H1 might be my favorite line, apparently, but it's absolutely not the only one. So we could change our view very slightly and for example, look at the sky in H alpha. So this is a line that we observe when hydrogen moves from between the third and second lowest energy levels of the hydrogen atom. Which means that when we observe the sky in this particular line, suddenly we see very different structures. We see all of these beautiful bubbles lit up within the galactic plane. So we can use a whole variety of different line emission tracers to study the gas in very different states, physical states, within our galaxy. And we could have a whole talk actually just on what we can learn from all sorts of different interstellar lines. But there's another very important player in the interstellar medium that I need to tell you about, and that is that the ISM is also filled with dust. This is another thing that I think needs a bit of a rebrand because dust does not evoke, good feelings for many people. Nor for many astronomers, but I think it's absolutely fascinating. So what I mean by dust is literally chunks of material with a typical size of order less than a micron, maybe 0.1 micron in size, of amorphous chunks of stuff, carbon and silicon and other elements, that is mixed with the interstellar gas and exists throughout actually much of the volume as that neutral hydrogen emission that we just saw. Dust is fantastically interesting as just a physical component of the interstellar medium. Yes?
Do you have any sense of like how many atoms is that in a small piece like that? I can't do the calculation.
Yeah, good. So you should think of this as being in sum about 1% of the about a dust to gas ratio of about 1 in 100. So there's a lot less dust, yeah.
Was that what you were asking, or the
But
size?
one of these particles kind of, how many atoms are in one of these things?
Gotcha. Oh, that's a great question. And the answer is actually extremely varied. So the absolutely smallest dust grains that we talk about are hydrocarbons, actually. So chains of order tens of carbon atoms, and those are sort of the, if you want to think of it this way, transition between large molecules and small dust grains. Those we talk about as being the very smallest dust grains, and then the dust grains that are responsible for most of the effects we're going to talk about today are less ordered in their structure because they're not forming this nice hydrocarbon ring, and they look more like amorphous blobs. In fact, let me just very quickly show you something that I stuck in my backup slides that is not, did I? Yes. Okay, this is not an interstellar dust grain because we haven't gone out there and gotten one, but this is a dust grain collected from the interplanetary environment of our solar system. So this is actually quite a bit bigger than a typical interstellar dust grain because it's able to grow to a larger size in the solar nebula, presumably. But you can see that it has this just amorphous, blobby structure, and that is a reasonable representation of what you should have in mind when I say interstellar dust grain.
And at that scale, is it more electrical attraction that's keeping it together than gravity or anything?
That's right. Gravity is playing no role in keeping it together. Yeah, good. Okay. Dust also has influences the light that we observe in various ways. So it's possible you've seen this image before. It's very famous. Has anyone come across this ever? I will say that I recently saw this floating around the internet with the headline, like, "There's a hole in space and astronomers don't know why." Something alarming and false. So this is an observation in visible wavelengths of light and slightly into the near infrared. So wavelengths of light quite similar to what we can detect with our human detectors, our eyes. And what you see here is, what you see over here are a bunch of background stars, and what you see here is an obvious lack of those stars, but not because there's a hole in space and we don't know why, not because there's an absence of stars at all, but because this is a region where dust in the interstellar medium is absorbing the light from the background stars. And so if you look in these visible wavelengths, we don't observe it. Dust in general absorbs and scatters light at particular wavelengths very efficiently, and so it is very good at changing the measurements that we would make in its absence. And that is why, actually, that is one of the reasons that dust can be a big nuisance for certain areas of astrophysics. But, you know, one person's trash is another person's treasure, I suppose. And the only thing you need to do to prove this to yourself is to change the wavelength at which you observe this patch of interstellar space. So if we're looking at very short wavelengths that are close to the size of the dust grain, basically, we will see this patch, this absence of light where it's very efficiently absorbed. And as we move to longer and longer wavelengths that are no longer efficiently absorbed by the dust, we can see right through this cloud to the stars behind. And of course, in addition to gas and dust, there is also interstellar radiation that is important for a lot of the physics that we want to figure out. And the interstellar radiation field, again, let's talk about the vicinity of the sun, okay? So our friendly neighborhood 1 kiloparsec or so is really dominated in the radiation field, in the energy density of radiation, by 3 sources of photons. So I'm curious if anyone wants to guess at what one of those 3 is. What'd you say?
The sun?
Oh, well, okay. Stars, yeah, exactly. Yeah, stars are absolutely one of the 3 most important contributions to the energy density of photons nearby. Any guesses at the other 2?
Solar wind?
Well, okay, broad neighborhood, right? Not right here. Although that's a good point. Okay, one of them we just talked about in the last few slides. Dust is also thermally emitting radiation, and that's actually an important constituent of the overall interstellar radiation field budget. And one of them I mentioned only super briefly. It's very old relic light from early in the universe. Yeah, the cosmic Gregory background. Yeah, exactly. Those 3 really dominate. Of course, there are many other sources of photons, and what dominates where will be a strong function of your exact position in the galaxy and of what wavelength you're looking at in general. And so that is what we can use to make observations of many different environments by using our full electromagnetic spectrum. But today's story is about the magnetic fields that really pervade this whole complicated medium, that pervade this space that's filled with this gas and this dust, and that is bathed in this interstellar radiation field. And the final point I want to make about the ISM as an object of study, before we get into how we measure magnetic fields in it, is that the ISM, the interstellar medium, is a particular environment that is absolutely influenced by the larger context that it sits in the universe. And so I really like this illustration of the interstellar medium in here in the disk of this galaxy, and how it is very intimately related to the more diffuse gas around the galaxy that we call the circumgalactic medium. And of course, far beyond that, to our intergalactic medium. So we in an even bigger picture context, we want to understand how it is that galaxies obtain and use and recycle or spew out their gaseous fuel. And within galaxies, one of the big problems that we are tackling in astrophysics is to understand how gas is cycled within galaxies to produce generations of stars that spend their lives within the galaxy and contribute energy and material back into the interstellar medium. And so we really think of a bit of a life cycle of gas as being the story of the interstellar medium over cosmic time. We really want to understand how it is that diffuse gas in the Milky Way can form pockets of gas that are able to become very cold and very dense and ultimately fragment and form new stars. And then we want to understand how it is that those stars are influencing their environment around them, sometimes gently contributing their stellar wind to their nearby environment, sometimes violently when massive stars explode into the interstellar medium at the end of their life. And when they do that, of course, they seed elements, they seed energy and momentum back into this general interstellar environment. And so we want to understand every piece of this puzzle individually and how this all relates together to drive galactic evolution, essentially. Okay. Now, finally, the moment you've all been waiting for, I'm finally going to explain to you how we actually measure these interstellar magnetic fields that are influencing this whole process, right? Basically, every step of this, okay, so not actually yet, every step of this cycle is influenced in some way by the presence of interstellar magnetic fields, and that's a big piece of the puzzle that we're still trying to understand. Okay, so how do we measure magnetic fields out here in interstellar space? Well, on Earth, if we want to see a magnetic field, say, of this bar magnet, we can just get some iron filings, sprinkle them around, and the magnetic field structure will be revealed to us, right? But obviously, we cannot fly around interstellar space dumping iron filings out the back of our spaceship, because space is far, far, far too vast, and also because that would be littering. But fortunately for us, we don't have to do that because the interstellar medium is dusty, right? We just talked about how this interstellar space contains a lot of these very tiny chunks of material that we call dust. And that turns out to be a key to several of the ways that we're able to measure interstellar magnetic fields. But the exact measurement that we're making is of the polarization of light. Remember, with very few exceptions, gravitational waves and particular particles being two of the obvious exceptions, most of the data that we have to work with as astrophysicists is light. Light in different wavelengths and light in different polarization states. And so very briefly, polarization is a property of light that refers basically to the geometrical orientation of the light wave oscillation. And so in a cartoonish way, we can describe, we can draw these arrows that are pointing in all directions to describe unpolarized light, has no preferential plane of oscillation. And then we can describe linearly polarized light as having this preferred direction, okay, this preferred orientation. This is maybe familiar to you if you ever have polarized sunglasses, because those allow you to see the beach out there on a nice bright day exactly by preferentially emitting only one polarization state of light, and in particular, light that is glancing off of the ocean or the road on a sunny day is partially polarized with an orientation that is horizontal, parallel to the ground. And so if you don't emit that polarization state of light as efficiently as you emit the vertical polarization state of light, suddenly you can see much more clearly. Right? Does that make sense? Awesome. So we are going to measure the polarization of light. And now you should be asking me, well, okay, fine, but what does that have to do with the interstellar magnetic field? And here's the key. Interstellar space is dusty. I am no artist, but here are my dust grains, okay? Each of these little blobs is supposed to represent one of these submicron scale chunks of material that, remember, in general, have an amorphous shape, which is to say that in general, they're not perfect spheres, right? And it turns out that these dust grains find a preferred orientation with respect to the interstellar magnetic field. Yes, I know, it's awesome, right? The very short version of that is that they're spinning, and their spin axis is the short axis here, and that spin axis is torqued into alignment with the local magnetic field. And so the average preferential orientation of interstellar dust, wherever it's sitting in interstellar space, is like this, orthogonal, with the long axis of the dust grain, orthogonal to the local magnetic field. And this is observable to us actually in two ways. One is that light from distant stars is in general, unless it's a weird star, in general pretty much unpolarized. But that unpolarized light is filtering to our telescopes through this dusty, magnetically aligned medium. And remember, that dust is absorbing wavelengths of light in the optical and the near infrared. And so if we observe starlight in optical linear polarization, we measure partially linearly polarized light where the polarization angle of that light, the plane of orientation, is imprinted by these magnetically aligned dust grains, selectively absorbing one component of polarization. Cool, right? Did you know this before today? Probably not. Great. And so quite literally, by measuring the polarization of starlight, we are measuring the orientation of the interstellar magnetic field. And this, by the way, this is the method by which the presence of the interstellar magnetic field was discovered. I think someone was asking me about that at the reception earlier. This is how it was first discovered, basically by observing a few stars that were nearby to one another, projected on the sky, but weren't necessarily physically associated with each other at all. You know, they could be at very different distances. And the observation made is that they all had very similar polarization angles. And the inference was that that's because it's nothing intrinsic to the stars themselves. It's this medium between us and the stars. And so we have the original discovery paper was something like 3 stars. I mean, and that was a science paper, you know. So we've increased our ability to make measurements of starlight polarization and really start to map out the magnetic field structure by making these measurements. Honestly, though, the number of measurements that we have of this is still pretty woeful, if you ask me. And there's an upcoming survey called PASIFY that's going to increase the number of optical starlight polarization measurements that we have looking up out of the galaxy, so looking at the more diffuse interstellar medium. It's going to increase the density of stars that we have there by orders of magnitude. It's going to be awesome. Yeah?
Does it matter what telescope or what instrument you use to do this?
Yes, that's a great question. Yes, you want to make these measurements ideally in the optical or the very near infrared, because that's where the dust is most efficiently doing the selective absorption. Yeah, great.
I have a question.
Yes, please.
Had I been studying this, I would have had a wrong intuition. I would have thought that about the fact that electric fields interacting with an anisotropic object could also align the object to the electric field. fields. And so how was it determined that it was the magnetic field that aligned these dust particles rather than the electric fields?
Yeah, that's a good question. So one answer to that is from just a purely theory perspective, that the net torque you see on a paramagnetic grain is what we think theoretically dominates this alignment. Now, a slightly more detailed version of this answer is that you could also ask, okay, there are many other processes that we could imagine could mess up this process. One is that for this to work efficiently, the dust grains need to be spinning. They're spinning because they're interacting with the interstellar radiation field. If we manage to get the dust grains somewhere where they're shielded from the interstellar radiation field, so maybe, deep in the interior of a molecular cloud, for example, could we make this alignment process either inefficient or dominated by something else? Right? Could we make it so that instead, the thing that punches these dust grains around and aligns them in a certain way becomes something set by the local velocity field of the medium, for example? And so the more detailed answer is that people spend their entire lives working on dust grain alignment theory. I mean, honestly, it's a very rich, very complicated, more or less classical, though slightly quantum also, physical system to study, and both on the pure theory side of things and on the observational side of things, trying to look for evidence that this could be, that at least in regions we could find an alignment dominated by something else, are both very active fields of study. So it's a fantastic question. Yes, great. And I should have said this to verbally input to make sure it's clear. Each of the little line segments in this now very old map of optical starlight polarization in our galaxy is the magnetic field orientation toward a star. But these dust grains also have one more piece of information to impart to us, or really a different way to reveal to us the orientation of the magnetic field that they're sitting in, because they're also thermally emitting radiation, as we talked about. And that thermal radiation is now also partially polarized because of this preferred alignment, now with a polarization angle that's basically parallel to the long axis of the grain. So 90 degrees rotated from the local magnetic field orientation that these dust grains are sitting in. And so when you look up on a nice dark night and you see the dusty band of the plane of the Milky Way, you can also think to yourself that if you could just change your wavelength sensitivity and instead observe in wavelengths dominated by this thermal emission from dust grains, what you would see is something like this. So this is an all-sky map, again, of emission at 353 gigahertz. This is a wavelength that is dominated by this thermal dust emission. These are measurements made by the Planck satellite, which is a recent European-led space mission. And Planck measured the whole sky at these wavelengths, also in linear polarization. And so the brush strokes that you see in the image here are a way of visualizing the measurement that we make. This is the inferred magnetic field orientation from measuring that polarization angle of light and then flipping it 90 degrees. And so that's what's visualized, overlaid here on the Milky Way. There's a little cartoon of Planck.
Okay.
Yeah.
You say the dust particles emit their own light.
That's right.
It's thermal radiation?
That's right. Yes.
What is the typical temperature of dust particles?
Ooh, great question. These are cold. These are typically approximately 20 Kelvin.
Sorry?
20 Kelvin. Yes. Yeah.
So they
20 to 30 Kelvin.
long wavelength light.
That's exactly right. That's exactly right.
Is the wavelength emitted larger than the size of the dust particle?
That's exactly right.
So they emit isotropically.
Yep. So exactly, right? So these data are 353 gigahertz, which is 850 microns wavelength, and this is not so exactly what you just said, right? The peak of the dust thermal emission spectral energy distribution is in the far infrared portion of the electromagnetic spectrum, and so it would be even better if we could make a satellite that observed at even higher frequencies. That would be actually, more toward the peak of the dust SED. But well, we'll take what we can get. These data are pretty spectacular. I've used them a lot in my own research. And I should really start to wrap up here, but let me just show you one more piece of eye candy, which is that we have very recently also been able to measure this polarized thermal emission from dust toward other galaxies as well. And so these are some data from a survey led by Enrique Lopez Rodriguez, who is currently a research scientist in the group at Stanford. You can see, if you look closely, the same sort of swirly pattern where we're visualizing again this linear polarization of the thermal emission from these dust grains. These were collected from the SOFIA telescope. There's me boarding SOFIA, which is or was, every telescope that I love ends, was until its mission ended very recently, a converted 747 with a hole cut out the side so that it could fly around in the stratosphere and observe, and it had an instrument on board that could observe this far infrared polarization. No, that was motorized, thankfully. Not out there with a winch.
So would the Webb telescope help you?
It doesn't have a polarimeter, sadly.
Oh.
I know. It's an amazing instrument. But it would be very nice to have a far infrared polarimeter to take up this cause, right? Okay, so I should end. Let me just super briefly tell you so that so we have some semblance of completeness here, that these aren't actually the only ways that we measure interstellar or astrophysical magnetic fields in general. We also have other wavelengths of light that let us probe different components of this rich multi-phase system. But these are the starlight polarization and polarized dust emission are the two of the most useful ways of probing the neutral, dusty interstellar medium, where a lot of the interesting physics for star formation and other cool processes is happening. So I hope when you go tell your friends about this for some reason, that you have now the three main takeaways that I set out to impart to you, right? The magnetic fields are ubiquitous in the universe, and that includes within the interstellar space of our own magnetic Milky Way, that space between the stars is not empty. It's actually full of fascinating, rich physical system that lets us study all sorts of interesting physics, including how it's influenced by these magnetic fields. And we have different ways of measuring magnetic fields, but one of the most prominent and useful ones recently is by the polarization of light imprinted by magnetically aligned dust grains in the interstellar medium. Thank you.
More questions?
I'm a little confused. I understand that you got your dust grains aligned and it's creating a polarized something. But how do you measure this polarization or these magnetic? How do you?
That's a great question. Yeah. Yeah.
How do you get what you need to draw these pictures?
Yes, good. So what we do is build detectors that have that emit one or the orthogonal polarization states of light, and so we measure basically we measure the electric field of the emission that is oriented this way, and then we clock that 45 degrees, and we measure the incident radiation, incident electric field this way. And from that, we derive exactly this polarization angle, which is to say, what is the net angle of the incident radiation. And it's partially polarized, right? So we also measure the total incident radiation. So we can also describe.
You're assuming that there's a 45-degree shift because of polarization?
No, I'm not assuming that. I'm just using that as my basis, basically. I'm just saying, like, give me the component this way and the component this way, and that is what I need to describe this angle. Does that make sense?
Is there a device that allows you to do this?
Yeah. Precisely detectors that admit and measure just a particular angle. Thank you. I don't know why that's the word that suddenly wouldn't come out of my mouth. Yeah, exactly.
And then there's another component to this, and that's the redshift, the Doppler effect.
That's right. Good.
So
Yes.
how do you deal with that?
Good. So that is exactly from the measurement that we make is the intensity as a function of wavelength or equivalently of frequency, right? And then we are converting that to units of the Doppler shifted velocity. These are all just equivalent ways of expressing the same thing, which is where is the emission as a function of spectral.
So now you're getting a 3D map of your magnetic field.
Well, we make that measurement for the line emission. Unfortunately, for the dust emission, we're just measuring this very broad band thermal emission, and so we're sort of stuck with this 2D projected imprint of the magnetic field. Now, a big part of my research has been exploring the connection between this 3D information we have in the gas distribution and the magnetic field, because it turns out that the structure of the gas is very closely linked to the magnetic field orientation. And so that actually gives us additional information that we can use to interpret the 3D, the otherwise unmeasurable three-dimensional structure of this polarized dust emission. And the one final thing I will say on this excellent question is that starlight polarization is also an important piece of this puzzle. It's showing us the same component of the magnetic field as the dust emission is, and it's showing us, more or less the same region, but it's not an integral out to infinity like the dust emission is. It's measuring the magnetic field in the dust in between us and the star. So if you also have a whole bunch of starlight polarization measurements, and you know the distances to your stars, which we're starting to know very well with this Gaia mission that has measured very precise parallax distances to a bunch of nearby stars, that is also letting you get some three-dimensional information on the magnetic field structure. And so that's like a major thrust of my current research.
So are you putting models together now, magnetic field models?
Let's have a chance for someone else to ask a question.
Ellen,
Yes, we know that the magnetic fields interact with, I'll call it ordinary matter, but do we have any idea that the magnetic fields might interact with dark matter? We know gravity does, but, and dark energy, of course, which we don't really know. But
yeah, it's a good question. I mean, so far we have no evidence for that, or else dark matter wouldn't be so dark, right? We don't have evidence that it's interacting electromagnetically. And one of the best pieces of evidence we would have would let us see it, right? But people come up with all sorts of models for dark matter, so we'll see.
So one thing you didn't touch on really is, well, earlier in your talk, you talked about how weak the interstellar magnetic fields are, and then your methods of detecting them. You know, you mentioned the Zeeman effect and then paramagnetism and these dust particles. Those are both pretty weak. In my field, we're like really happy if we can measure polarization, orientation effects to like a degree or two. I'm guessing you're much, much smaller. How do you achieve that sensitivity?
Oh, that's a fantastic question. Okay. The very weak interstellar magnetic field strength is a real limitation for our Zeeman measurements. The Zeeman measurements, if you can make them, are giving you direct information on that field strength, but they're very hard to make. They take a lot of telescope time. They take just absolutely rigorous control of your instrumental polarization of your system. And so that's difficult. We would like to have more and better measurements. These two methods that have to do with dust are actually pretty insensitive to the field strength itself because this magnetic alignment is so efficient. And so these weak order microgauss fields are more than enough to align these dust grains. And then what it comes down to, what your measurement precision comes down to, is how well you can measure this angle, and also how well you can measure the component of your polarization that's polarized, because it's just partial polarization, right? And that requires just fabulous calibration of your instrument. That's the main thing.
There's a question here first.
You've presented a very interesting case on how you measure all of these fields. And generally, when you do that, you're measuring for a reason to learn something about the sources of the fields, but you've never hinted at any direction as to, are you, I assume it's a composite of a zillion different things that are forming these fields, but why the measurements? What are you
Good. Thank you. Thank you. And you're right. There are several different answers I could give you to that. My motivation for some of these detailed measurements that I showed you today is to understand how gas in galaxies moves between these very different phases that we observe it to exist in, these very different thermal states, and ultimately how it's able to form new stars. That's a partial answer. We'd also like to know in more detail, how is it that galaxies like our Milky Way came to have these very well-organized large-scale magnetic fields? So actually a lot of what we are talking about at this conference connects to that question, because one of the things we want to understand is how turbulence in the interstellar medium might be able to convert energy of motion into magnetic energy in the interstellar medium, and how that might be very important for growing the field strength that we observe to exist in galaxies today. So it's a very open question theoretically that we're also needing to constrain better observationally. Yeah, thank you. Good one.
Yeah.
Do you suppose that microwave background radiation has a magnetic field? That would be interesting because it's a very change in the physics of the universe at that point.
It is a great question. So this is also a very open question in the field, right? When and where in the history of the universe did we first form magnetic fields, and were there truly primordial magnetic fields from some symmetry breaking in the very early universe, for example, or did everything of astrophysical relevance today, was it really seeded much later at the time of birth of structure in the universe? Open question. This field is honestly full of open questions in a good way.
So the Earth and the stars, I guess, can flip their magnetic poles. Can the galaxy?
That's a great question. Can a galaxy? You know, we do think, let me tell you what I think we have a decent handle on. Those systems aren't dissimilar in the sense that we think that the galactic magnetic field structure was built up by dynamo action. Exact way that we know to generate and keep sustaining these magnetic fields of stars and planets. But it seems to be quite important. They're also very different in another important way, right? Which is that those systems have these large convective regions that are important for the generation and an ordering of the magnetic field structure. And I don't think there's an obvious analogy to the galactic scale magnetic field to be made there, but the analogous, very interesting question that we definitely do talk about all the time is what actually is the picture? What actually is the dynamo action that can create these large-scale coherent magnetic fields in galaxies? And that we need observations of, we need to better understand the 3D structure of our own galaxy's magnetic field. It's the only galaxy we're ever going to see from the inside. We need more of these measurements of external galaxies, and in particular, we'd like to observe a broader range of types of galaxies, and a broader range of redshifts, so we have a better idea of how these magnetic fields grow and evolve over cosmic time. And then we need better theory, honestly. Like we here are talking about what actually is important for building this dynamo, and it's still a very active area.
Final question.
Okay, well, the light on its way to us must travel through areas of space with different orientations.
Yes.
I mean, what you're seeing is the sum total of all of these, so how do you decide?
That's exactly right. That's exactly right. You're seeing basically a density-weighted integral along the line of sight.
Integral of the whole path.
That is precisely right. And that's why, if we want to disentangle effects imprinted by the 3D structure, we need additional information. We need this work that I'm doing on the neutral hydrogen emission. We need 3D measurements of the influence of dust on stars, both through this starlight polarization and also just through the reddening of the starlight. Those three things combined can help us build up a picture of where the dust is along the line of sight, and also of the local magnetic field orientation that dust is sitting in. And that's ultimately one of the things we want to solve.
So different frequencies behave differently at different distances.
It's also helpful
figure that out.
It's also helpful to look at different frequencies, because if the dust is at slightly different temperatures, for example, then its thermal emission is going to peak in a slightly different place, and that can also give you some additional information, at least in principle. Yeah.
Okay, let's